uh, we have one final speaker. So this let me call on Dr. Edwin Sybingco. Our Dr. Edwin Sybingco has extensive experience both in industry and academe. He was the managing information system consultant of Phil-Pacific Apparel Corporation. Was also the technical trainer of the Dinso Techno Philippines Incorporated. Is also a consultant, electronics engineer consultant of the E6 Corporation. And he is an exchange scientist in Tokyo Institute of Technology. He was a visiting researcher in University of New South Wales School of Mechanical and Manufacturing Engineering. Currently, Dr. Edwin Sybingco is Associate Professor of the Department of Electronics and Communication Engineering at De La Salle University. Edwin, please. Hello, Edwin.
Okay, so again, thank you, Dr. D, for that introduction. So again, good morning and welcome to the last talk on computer science, machine learning, and artificial intelligence parallel session. My talk today is entitled Remote Controlled Surface Vehicle for LabLab Algae Harvesting with DSP Assisted Navigation. So here's the outline of my presentation. First, I will talk a little bit about what is LabLab. And then, of course, the challenges in harvesting LabLab based on our several discussions and consultations with the farmers in one of the farms in Hagonoy, Bulacan. Then I will talk about our proposed solutions to harvest LabLab. And then from the requirements, we came up with the specifications and design of the harvester. The design is then implemented and, of course, initially tested in the swimming pool. Now, of course, after several testing, we had the opportunity to test the surface vehicle in one of the ponds in Hagonoy, Bulacan. I will talk about the comparison between the manual and our proposed LabLab harvester. And of course, I will give some acknowledgement to the different institutions and our industry collaborator for supporting us in building the first successful LabLab harvester in the country. Okay, so what is LabLab? It is essentially an algae mat, colloquially called LabLab, which is a combination of microscopic algae that usually grows in fish ponds. In the Philippines, this LabLab is an excellent source of organic nutrition for aqua feeds. The video on the left shows how the LabLab separates from the soil, and it is very easy to cultivate, but the following are the challenges. First, it lacks harvesting and drying methods to address its seasonality. Second, its biomass tends to dissolve easily when agitated. And for the local, it is usually used by traditional farmers to feed milkfish. And then, of course, our industry collaborator, Sante, it is a company that produces aqua feeds, and even Sante recognizes the challenges in harvesting LabLab, which became an opportunity for us to develop several methods of harvesting and drying LabLab. The team of Dr. Alvin Culaba establishes the Big Hub to address these challenges, and you can find more information about our Big Hub in our websites, www.abighub.org. Now, as mentioned, LabLab needs to be cultivated and harvested efficiently and processed into pelletized feeds, which is usually used as feeds for the milkfish. And to understand its importance, shown in this chart is the market share of, let's say, milkfish in the country compared to other farmed fish. Its market share is 36%, which is equivalent to 401,600 tons in 2013. Now, from the challenges mentioned, we identified the following objectives for this project. First, to develop a machine to efficiently harvest LabLab using robotics and, of course, artificial intelligence. And then second, we want to, let's say, encourage other LabLab researchers to further improve our proposed harvester, as this is the first and only successful automated harvester of LabLab in the country. And finally, most importantly, to increase the sustainability of the pond and the cultivated LabLab. Now, shown here is the location site of the farm in Barangay Parong-Parong, Bulacan, where we have the opportunity to apply the harvester, which is around 54.8 kilometers from De La Salle University. On the right is the exact farm where we actually tested our harvester. Now, here is the design of the surface vehicle with the following dimensions: around 26 inches wide, 53 inches length, 36 inches height. The harvester is around 17 inches height from the water. Shown on the right is the efficient and effective harvesting mechanism installed on the surface vehicle. We use the 125 micron wire mesh as the floor mat of the conveyor system and the DC geared motor to move the conveyor system. We have experimentally verified that by using the combinations of 125 micron wire mesh and the DC motor, we are able to collect the LabLab successfully from the water, as shown in this video. This experiment was conducted last January 27, 2019. Now, after the design was completed, the surface was implemented as, let's say, shown. So this is now the actual surface vehicle with the harvester. Of course, initial testing was conducted in the swimming pool, as shown in this video. Now, the controller used to move the vehicle is the Pixhawk. We usually use Pixhawk in our drone projects, but in this project, we have implemented it in the surface vehicle. The controller has two communication links, the remote controller receiver that is used to communicate with the remote controller. And of course, we have here the telemetry to communicate with the ground stations. And from the telemetry, we are able to monitor the battery status of the surface vehicle, the GPS locations, the roll pitch yaw from the IMU or the internal IMU of, let's say, the Pixhawk. And then connected to the controllers are actually the brushless DC motor and, let's say, the servo motor to essentially control now the dynamics of the surface vehicle. Now, between the Pixhawk and the brushless motor, we have the ESC, which is actually the electronic speed controller. Shown on the right is the actual implementations. You could see now the Pixhawk, the telemetry, the battery, and then, of course, some connections. Now, shown in this slide is the propulsion and steering control. The steering is controlled using the servo, while the propulsion is controlled using the brushless motor connected to the 3-blade 40mm water jet pump thruster. Now, there are two modes of operation. Mode 1 is the remote control, and the driver usually, essentially use this remote control to maneuver the surface vehicle. While mode 2 is the autonomous. Now, in the autonomous, we use the mission planner to define now the mission through the so-called waypoints. So, for example, in this, let's say, figure, we specify the longitude and latitude of the waypoints labeled as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and finally 11. These waypoints are uploaded to the surface vehicle, and when operated in the autonomous mode, it will follow the program path. Shown in in this particular, let's say, slide is the test where we are able to operate the surface vehicle in the autonomous mode. The waypoints that we specified here resulted to a path that is actually circular in manner. So shown in this video is the ability of the surface vehicle to essentially follow the program path. The surface vehicle is also powered by a vision system. The vision system is used to detect now the presence and concentrations of the LabLab as it moves. So as of now, the vision system is used to assist the driver in navigating the surface vehicle. But of course, in the future, we plan.
Edwin, we lost your sound. Edwin?
Can you hear me now?
Okay, you're back.
Okay. So let me go back to my presentation. Sorry about that for the technical issue. So anyway, I think you weren't able to, let's say, listen to this slide, right? So the surface vehicle, as mentioned earlier, is also powered by a vision system. The vision system is used to detect now the presence of, is used to detect the presence of the presence and concentrations of the LabLab as it moves. And as of now, the vision system is used to assist the driver in navigating the surface vehicle. But in the future, we plan to correlate now the amount of LabLab harvested with the detected LabLab as it moves to the PAMS. Now, from the testing that we have performed, shown on the left is the original video.
We lost you again, Edwin. We cannot hear you anymore, Edwin.
Sorry. Okay, can you hear me now?
Okay. Okay. You're back.
I'm back. Okay, so I think it's because of the video material. It's eating up all the bandwidth. So anyway, as mentioned earlier, we did the testing. The left video shows the original video, and then the middle one is the annotated versions. And then essentially to get now the ground truth of, let's say, the presence of the LabLab, and then the right video will actually shows you the detected LabLab. We use now deep learning to, let's say, detect now the presence of LabLab. And the accuracy we got is 97% without LabLab and 90% with LabLab. Okay, shown in this figure is the testing of the surface vehicle to harvest the LabLab. The surface vehicle moves up and down, and each lap is one run. Shown in the image are the presence of LabLab before run 1, and then this is now after run 1, after run 2, after run 3, after run 4, and finally after run 5. Now, shown here in this figure is the comparison between the manual harvesting and our proposed harvesting.
Edwin, please share that one. We cannot see it in the screen.
Ay, sorry. Uh, let me go back. I think. Sorry for that. Okay, let me share this back again. Okay, so this is essentially the video that compares now the proposed harvester and the manual harvesting. Okay, so to quantify now the comparison, the proposed method is able to complete the harvesting for 5 minutes in a 15 feet by 25 feet pond, while the manual harvesting was able to finish it in 30 minutes. So now I'd like to acknowledge the following institutions and industry collaborators for their support in this project. First, the Center of Engineering and Sustainable Development Research, or CESDAR, of De La Salle University. Second, the funding and monitoring institutions, the OST, specifically the Philippine Council for Agriculture, Aquatic, and Natural Resources and Development, or PICARD. And of course, finally, our industry collaborator. Now, here's the picture of the research team who works on this project. So again, thank you for listening, and again, good morning. Sorry for the technical issues that I had earlier. Thank you.
Okay. Thank you very much, Dr. Edwin Sybingco, for that very nice presentation and interesting. So this is the first LabLab harvester in the Philippines. And I'm sure there's a lot of business opportunities for this. So with that, we are late by almost 50 minutes. So I'm sure, guys, you are tired. But let me finish by telling our deepest gratitude and thanks to all the presenters. Despite their hectic schedules, they were able to join us and present their research, as well as share their expertise to this parallel session 5.2 of our 40th PAASE anniversary and 2020 APAMS annual scientific meeting. So on behalf of these 5.2 committees, I would like to thank also all the participants. I hope you learn a lot from this web conference. And if you have questions, I'm very sorry that we're not able to have a live questions, but the speakers are willing to entertain it via their email address or the chat room. So thank you very much once again. And I'm going to end this session now. Moon?
Thank you. Thank you.
our discussion.
Yes, sir. Dr. JP, please.
Alvin.
Thank you, Elmer. Thank you, thank you, everyone.
Okay.
Excellent. So I listened until the end. So very good. We can compile. Anyway, there's a recording, pare. So I requested Richmond to provide us a copy so we can share it to people. Okay. Congrats, pare, and the rest of the team, and Neuron and everyone. Thank you. Thank you, Chong.
Mon, Richmond, thank you very much. And Giselle also, thank you.
Yeah. Thank you, Giselle. Thank you, Mon. As usual. Okay. Nandiyan pa si Ralph, Joel, and
umalis na si Joel at saka si
was
Rob.
na? Okay. Sige. Thank you, Edwin. Dalawang Edwins. Lawrence, Robert, Ryan, Argel. Thank you.
Okay. Bye-bye. Stay safe. Chong, you have to schedule.
Yes. Yeah. Yep. We will. All my students attended the talk. So we will. Thank you for all my students. Thank you. Everyone attended the talk till the end. Thank you.
Okay, Chong. Bye-bye.
Bye. Ingat kayo.